Hey, this video is going to help you learn how to do mass-to-mass stoichiometry problems. So in order to do these problems, you're going to need a periodic table and your calculator. So get those and have those at hand so you can follow along with this lesson. Okay, so what we're going to look at with this is first we're going to look at the law of conservation of mass, and then we're going to solve some mass-to-mass stoichiometry problems. Stoichiometry is Greek for measuring elements. And what we do with stoichiometry is we can calculate quantities of different chemicals and chemical reactions when we use a balanced equation. And balanced equations help us figure out how much of one substance we need or how much will be produced when we are looking at a balanced equation. And you actually do stoichiometry in your everyday life, you just don't realize it. If I were to ask you about how many pieces of bread you would need to make a sandwich, you would tell me 2 pieces of bread. Okay, so 1 sandwich, and from there you could predict you would need 2 pieces of bread. Now, when we look at a balanced equation, it's this coefficient that represents moles or particles. Now, I never really told you what the big number in front meant, the coefficient, when we were balancing equations. And part of that reason is because it can mean a couple of different things. It can be moles or it can be particles. And remember, particles can be atoms, molecules, or formula units. And as long as the coefficient numbers remain proportional, the equation remains balanced. So again, if I want 1 sandwich, I would need 2 slices of bread. Okay, so 2 pieces of bread. Okay, my little dot there is freaking out. Okay, I would need 2 pieces of bread. There we go. Okay, if I wanted 10 sandwiches, let's say I wanted 10 sandwiches, then you know I would need 20 pieces of bread. Okay, that's stoichiometry. Like I said, you've been doing it all along, you just didn't realize it. We're using one piece of information, one quantity, to predict what we're going to get out of it. So oftentimes recipes are stoichiometry, or even different things like 1 car needs 4 tires. Okay, it just doesn't have to be cooking. So, like I said, at first we can look at those coefficients in terms of particles. So if I look at this here, 2 molecules of H2 plus 1 molecule of O2, because I have my invisible 1 there, forms 2 molecules of H2O. If I change the 2 in front of the hydrogen to a 4, what would happen to the other numbers? Well, if I make this a 4, then this is going to double to a 2, and that's going to double to a 4. That's what's going to happen to the other coefficients. So that's one way to look at it in terms of particles. I could even take a look at it in terms of Avogadro's number. What if I change the coefficient in front of oxygen to 6.02 times 10 to the 23rd? Well, then these two things would adjust proportionally also. I would have 6.02 times 10 to the 23rd molecules of oxygen, 12 times 10 to the 23rd molecules of hydrogen, and then the same thing, that 12 times 10 to the 23rd molecules of hydrogen. I still have that 2 to 1 to 2 relationship. And so as long as the proportions within the equation remain the same, then my equation remains balanced, and I can keep making my predictions. I can also look at it in terms of moles, and honestly, this is how we often look at it. It's those coefficients that tell us how many moles of each substance. So again, 2 moles of hydrogen, 1 mole of oxygen, and 2 moles of water. Right, so moles is another way we look at it. The third way we look at it is in terms of mass. This is not the first time you've looked at the law of conservation of mass. And what it says is mass is neither created nor destroyed, it's always conserved. So our simple way of putting it is what you start with in terms of mass. Oops. Start. Okay, so what you start with is what you end with. Okay, so the mass you start with has to equal the mass you end with. And so that's what I'm going to show to you on the next couple of slides. So if we take a look at this reaction here, nitrogen plus hydrogen makes ammonia. NH3 is also known as ammonia. That same stuff that's used in Windex. If I want to look at it in terms of atoms, I have 2 nitrogen atoms plus 3 times 2, 6 hydrogen atoms, and it makes a total of, well, here's 1 nitrogen and 3 hydrogens, that's 4 times my 2, 8 atoms in the ammonia. And right here where my arrow is, I could put like a heavy line or a squiggly line to show you these are my reactants on this side here. These are my reactants and these are my products. So law of conservation of mass says the number of atoms I start with has to equal the number of atoms I end with. So I have 2 atoms of nitrogen and 6 atoms of hydrogen, and that does essentially equal 8 atoms making up my ammonia. Now, if I look at moles, again, I have this invisible 1 in front of the nitrogen. I have 1 mole of nitrogen plus 3 moles of hydrogen makes 2 moles of ammonia. Notice that these things don't equal. The 1 does plus the 3 makes 4. But instead, on this side, we have 2. So it doesn't look like moles are conserved. We could also look at it in terms of particles. If I put in Avogadro's number, so 1 or 6.02 times 10 to the 23rd. But I'm going to keep the number simple. I'm just going to call it 6 times 10 to the 23rd. So if I had 1 mole of the particle, 6 times 10 to the 23rd, here I've got 3. If I do 6 times 3, that's 18 times 10 to the 23rd. And then over here with the 2 in front of the ammonia, I would have 2 times 6, which is the same as 10 times 12, or I'm sorry, 12 times 10 to the 23rd. Getting my numbers confused there. Okay, so does not equal again. The last way we want to look at it is in mass. I have 2 nitrogens, and remember nitrogen's 14.01, so that's 28.02. Okay, and then I have hydrogen, and 1 hydrogen's 1.01, but I have 6 of them, so 6.06. And then with the ammonia, I have 1 nitrogen and 3 hydrogens. I add those up, and that's 17.04. I multiply it by 2, and what I get is 34.08 grams. And all these down here at the bottom are grams. So if I look at my total mass of products, I only have 1 product, and it is a mass of 34.08 grams. And if I add these 2 numbers up, and let me circle them in a different color to make it stand out better. Okay, if I circle these 2 here and add those 2 numbers up, those are my reactants. And what we find is those are equal to the products. And so that shows you the law of conservation of mass. I have the same number of atoms, and I have the same mass at the beginning and the end of the problem. Not necessarily the same number of moles, not necessarily the same number of particles. I could also look at liters, 22.4 liters, but I'll give you a hint, it doesn't work out. Okay, so that's one way to show it using that information from a chemical reaction. Okay, so you try one. This is arsenic triiodide. Okay, arsenic triiodide. This is iodine off your periodic table. So pause this and I'll let you take a look and see how you can fill this out. Okay, so here's what you should have gotten for your answers. You should have a total of 8 atoms right here, 2 arsenic and 6 iodine. And on this side here, you have 2 arsenic and 6 iodine, a total of 8 atoms. 2 moles from your balanced equation right there, 2 moles of arsenic, 3 moles of iodine. Okay, and then that multiplies times the 6 times the 23, so 12, 12, 12. Notice again, these things aren't working out, but my atoms are conserved, and again, my mass is conserved. I end up with 911.24 grams. So atoms are conserved, mass is conserved. Moles and particles are not. So that's what it tells you right here. Molecules, formula units, moles, volumes, which is another way of saying, you know, we typically measure it in liters, will not necessarily be conserved. You could have the same number of moles at the start and the finish of an equation, but if you do, it's just a coincidence. It's not because that's the way it was supposed to be. Now, for the most part, when we're doing these, we're going to treat the coefficients in a balanced equation as mole ratios. So we're going to think of these numbers in front as moles. So we're going to write some mole ratios here to start. So I want a ratio of iron to copper sulfate. So I just look at my iron, 2 Fe to my copper sulfate. Well, in front of my copper sulfate, I have a 3 CuSO4. So this colon demonstrates a ratio. So essentially 2 irons to 3 copper sulfates. If I look at my next one, iron to iron 3 sulfate. Well, again, I look at my iron right here, and I have 2 irons to, now here's my iron sulfate. Remember, the number in front is an invisible 1, to 1 iron 3 sulfate. Okay? So again, I'd like you to pause the video and try these next couple. Do them on your own. The last ones down at the bottom are just another way of showing ratios. Okay, so now you should have your answers. You have 2 Fe to my copper to 3 coppers. Then I have 3 moles of the copper sulfate to 1 mole of the iron sulfate. There. Okay, and then with my copper sulfate, 3 copper sulfates to 3 coppers. And then lastly, 1 iron sulfate to 3 coppers. You might notice that here you could reduce it. It is technically a 1-to-1 relationship, but when you are doing your assignments and you are doing your online practices and exams, do not reduce it. Actually write it as 3-to-3. Don't reduce it down to 1-to-1. It's okay when you're solving the math to reduce it, but right now we just want to set it up and make sure we don't mess up our proportionality. So don't reduce those numbers. So that was the last thing that we needed to help us figure out these different parts. Okay, this is the mole roadmap that I showed you guys last week. We can look at volume in terms of liters, 22.4, mass in terms of grams, and we get the molar mass off the periodic table. And when I'm talking about particles, remember particles are atoms, molecules, or formula units. That's when I'm going to use 6.02 times 10 to the 23rd. And everything relates back to 1 mole. So that's what I'm going to compare it back to. That's what we were doing before. Stoichiometry has one more added step using that mole ratio. So while this diagram may look scary, what you might realize is this is one of those mole roadmaps drawn together, and this is another mole roadmap all drawn together. Okay, so all I did was kind of squish it together. And the only thing new and different in this one is this mole ratio. That's our 4th step. So in this presentation, we're going to take everything from mass, we're going to change it to moles. So mass is 1 step, moles, my mole ratio, and then there's my 4th step right there. So again, if I want to divide this in half, this would be chemical 1, And this would be changing it into chemical 2. Because again, what's different from this this method to the last one we learned, the last one we were staying with the same chemical. This one we're changing one chemical to another. And what's going to help us do that is the mole ratio. So it's really important when you do these, well, first we want to read the question, but then to check our equation and see that it's balanced. You'll always be given an equation for one of these or be told to write one. So if 10 grams of iron are added to a solution of copper 2 sulfate, how much solid copper will form? Okay, so here's my equation that's provided to me. I do check it, and it is balanced in this case. This is the same equation we used for the mole ratios. So if I have, here's what I'm given to start, 10.1 grams, and then my, oops, not this there. Okay, the question asks how much solid copper will form. So the way I set up these problems sometimes is I write the stuff on top of it. Since I'm given 10.1 grams of iron, I write that there, and then I am asked for grams of copper. So I put a question mark with the G next to it. So just like before, you always start with what you're given. We always do our units first. So 10.01 grams of Fe. I draw this out. It's going to be a longer problem. Diagonal down, same units, grams of Fe. Now, when we looked back before, the only place you can go from grams is to moles of the same exact chemical. So that's what I'm going to do. I'm going to go to moles of Fe. Draw my line, diagonal down, same units. Now at this point, I'm at this mole ratio. I can change my chemical. This is chemical number 1. This is chemical number 2. Okay? So I can change my moles of Fe, which is what I'm given, to my moles of my copper, which is what I'm looking for. So moles of copper. Diagonal down, same thing, moles of copper. And then finally in the last box, I get to put in what I'm looking for, which is grams of copper. Now, just like before, you just want to worry about 2 boxes at a time. So we're just going to look at these first 2 boxes right here with the moles and grams. We've done this before, okay? We've had these comparisons between moles and grams. So moles is always a 1, and grams comes off the periodic table. And with iron, that is 55.85. So let's do the other one at this end, moles and grams. Moles of copper is a 1, and looking at the periodic table, we get copper's molar mass, which is 63.55. The last thing I need to do is fill in my mole ratio, and my mole ratio is when I have moles on top of moles. So right here on top I have moles and copper, so I'm going to take that coefficient of 3 and put it right there. Moles of copper. And here's my moles of iron. There's my moles of iron right there, and I'm going to fill that in. Now when you solve this, you want to multiply the numbers across the top and divide by the numbers on the bottom. So I'm going to show you how to enter this in your calculator very simply in order to get the right answer. Okay, so this is what you want to do. 10.1 times 3. So I'm going to do it too. 10.1 times 3 times 63.55 divided by 55.85 divided by 2. And what you get is 17.2387 and some more numbers that we don't need. Okay. We want to look at our sig figs. I'll switch my pen color again. Let's look at the sig figs. Here, with the 10.1, I have 3 sig figs. My 55.85 is 4. This one's 4. My 1s are infinite. So the thing that's new is this mole ratio right here, the 3 and the 2. And the question you ask yourself, is this an exact number? 3 moles to exactly 2 moles of iron, and that is true. So both those numbers are infinite. So we want to round our answer to 3 sig figs. So I'm going to take the first 3 numbers, look at the number after that. It's a 3, so no rounding. So 17.2, and my units are whatever's here, grams of copper. And that is your final answer. So what this is telling you is if I took 10.1 grams of iron, how much copper would I get? Well, I'd get 17.2 grams. It's like saying if I took 6 slices of bread, how many sandwiches would I get? I'd get 3 sandwiches. Hey, so let's do another one here. How much iron is needed to produce 15 grams of copper when excess copper 2 sulfate is present? So right there it tells me, there's my question, how much iron? And again, it's a solid mass, so we're going to measure it in grams, is needed to produce 15 grams of copper. So you can see it almost looks like we're going to work it backwards, but not really. It works out the same way. This time it's like saying, hey look, I know I want 15 sandwiches, so how many slices of bread do I need? It's that same idea. We still start with what we know, in this case 15.0 grams of copper. So nothing changes there. So diagonal down, same units, grams of copper, grams changes to moles of the same element. Diagonal down, same units, moles of copper. Now when I have the moles down here at the bottom, I can change it to moles of what I'm looking for, moles of iron. Diagonal down, moles of iron to grams of iron, which is what I was looking for. Just look at it 2 boxes at a time. I've got moles on top of grams. When I have moles and grams together, moles is a 1. Grams of copper off the periodic table, 63.55. Here at the end, moles and grams. It really does not matter what order you fill the boxes in. Okay, grams of iron. What was iron? It's 55.85. Yep. Okay, so 55.85 for my grams of iron. Here's my mole ratio. In front of the iron, I have a 2. In front of the copper, I have a 3. Multiply the numbers across the top, so 15.0 times 2 times 55.85. Hit divide for all the numbers on the bottom, so divided by 63.55 divided by 3. And I'm going to write it here at the top. This is what you get, 8.7883. And again, more numbers than we need. Okay. We take a look at our sig figs. Again, my molar masses have 4 sig figs. All the whole numbers are infinite. It's my starting mass that gives me 3 sig figs. So I'm going to keep the first 3 numbers and look to the next number to round. So that becomes 8.79. That 8 rounds up the other 8. And my ending unit here is grams of Fe. Okay. So how much iron is needed to produce 15 grams of copper? If I want 15 grams of copper, then I need to start with at least 8.79 grams of iron. Okay, the last one is meant for you to set up. How many grams of sodium chloride are produced from 7.5 grams of sodium and excess chlorine? So with this one here, remember your first step is to always make sure your equations balance. Sometimes I balance them, sometimes I don't. Okay, you have a mix of them on your assignment. So you've got 1 sodium, 2 chlorines, oops, only 1 chlorine. So we need to fix that. 2 sodium chlorides. So that gives me 2 sodiums here, so I need to put 2 sodiums there. And now I have a balanced equation. So at this point, I'd like you to pause and try and set up the problem. So I am given 7.5 grams of sodium, and I am asked for grams of sodium chloride. So 7.5 grams of Na. And I'm just going to set this one up a little different to show you an alternative setup. Some people don't like this T-bar picket fence formation like that. They feel it's messy. So I'll show you an alternative way. So same thing, diagonal down, grams of Na. Grams of sodium can only change into moles of sodium. Diagonal down, moles of sodium. Moles of sodium change to moles of what it is that I'm looking for, moles of sodium chloride. Okay, diagonal down, moles of sodium chloride, NaCl. Finally, to grams of sodium chloride. Okay, so there's your basic setup. It's the same thing as the T-bar formation, but this time they just spaced it out. It looks like ratios. Your teacher's just lazy, and so are other chemists, so they like to write it like that. So same thing, grams, grams, moles, 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 grams for those problems. Okay? Now, I'm not going to fill in the numbers. So you're going to have to fill in the numbers and finish solving this problem yourself. Okay? The following lesson has to do with showing you how to get moles and liters. If you can grasp the grams to grams ones, then solving for moles and liters is quite simple. Be sure to complete your summary at the end of your notes. That's something that will be checked in addition to your problems.